My name is Thorsten Höfler, and based on some requests, I'm now recording this arming GPUs for impactful sciences with the GH200 Superchip talk and true Exascale that I gave a couple of weeks ago as a random access talk in the DOE Salishan meeting 2025. So what was that meeting about? That meeting was actually focused on the Exascale computing project, talking about Exascale. There was a panel, Reflections on Exascale, and there was another session, Applications using Exascale machines. So at the end, that whole meeting focused on Exascale. In this talk, I will give you a little bit of an insight what we have done to achieve Exascale and how we could actually go forward, and also the future and the present and future of the GH200 Superchip. So I want to actually highlight this paper where we looked at the details of this chip, tightly coupled, one of the first tightly coupled heterogeneous systems that we have available at large scale, and especially also in Switzerland. So what is the anatomy of one of those chips? It's quite a complex device. So what we have first is we have on the left side the Grace CPU. That is an ARM CPU with SVE extensions, a relatively powerful little CPU. And then on the right side here on this die shot or package shot, we have the Hopper GPU. So these are actually connected with an NVLink C2C interconnect, which is 450 gigabyte per second per direction. This is not the standard NVLink interconnect. It's called NVLink C2C for a reason, because it is a proprietary interconnect that connects these two. Well, NVLink is also proprietary, but this is another one that specifically connects CPU and GPU for all kinds of different coherency reasons. What you have then on the CPU side, you have pretty massive low power DDR5 memory banks that give you up to 500 gigabyte per second bandwidth, which is not the highest bandwidth in the chip, but the highest capacity in the package. And then, of course, on the Hopper side, you have extremely fast HBM3, so 4 terabyte per second total bandwidth into this. And in total, you have nearly 20 terabyte of shared memory per memory domain in the networks or in the systems that we deploy. So now, the whole system itself is a NUMA system. So here on the left side, we actually have NUMA domain 0, and here on the right side, we have NUMA domain 4. Now you may wonder, where are the other 3 NUMA domains? Well, they're actually in the other chips of the system that I'm describing. So here we have the Grace NUMA domain 1, Grace NUMA domain 2, Grace NUMA domain 3, and then the Hopper goes in strides of essentially 8 forward, so 12, 20, and 28. So now this is a full system that combines 4 of these Grace Hopper Superchips into one domain. What is a domain? Well, a domain is connected by the NVLink interconnect, and now this is the standard Hopper NVLink interconnect. And here between each pair, you have 150 gigabyte per second per direction, which again means 900 gigabyte per second total. But now this is 4 times 150 gigabyte per direction times 2, and so, or actually 3 times that much, because you in order to connect 4 chips, you only need 3 links each. Then the second thing is, which was kind of the surprise interconnect. At the beginning, it was not well documented. We found it through measurements, and we convinced NVIDIA to release this. And so this is the Grace interconnect. This is the interconnect that connects the CPUs, so the Grace pieces among each other. And that only has 150 gigabyte per second total. So that is significantly slower, actually. So if you communicate from Grace to Grace, it is significantly slower. And then at the end, each of those are connected with a slingshot network. That is now the global interconnect, where you connect a large cluster. In our case, we have more than 10,000 GPUs total, with more than 4,000 nodes of this type containing 4 GPUs each. Okay, wonderful. Now you realize, well, this is extremely complicated to program this device. In fact, I'm going to make a longer talk on how to exactly do this. We could now talk about different latencies we could talk about how they're actually connected. I mean, what is the peer latency between 2 different chips? We could talk about the performance of unified memory. We could talk about how many threads you actually need to violate to achieve the bandwidth. And we could talk about many, many, many other things. So unfortunately, it even matters which pairs are specifically communicating. We could talk about the communication properties over wider networks, so for example, over MPI, and many, many, many more that I don't want to talk about in this very short talk here that I gave at the Salishan meeting. So actually, this whole thing is even more complex than this. So if you're interested, you could look at the paper. You will actually find what happens if you if you use different memory allocation APIs to allocate the memory that you're communicating from and how that influences your bandwidth. And at the end, you will realize, well, this is extremely complex to program. So how do we now program this device? Because now it matters how we allocate, what are the communication pairs, how do we lay out my memory, what do I put on the CPU, what do I put on the GPU? And this is just some of the factors that you need to consider to get the highest performance for this particular device. Well, again, if you would like to learn about all of this, I would recommend reading this paper. It's quite detailed. It has essentially measured all the combinations you can imagine, lots of data in the paper, and it will give you some insights on how to program this device if you have to. But I want to go back to Salishan, because actually at the first day of Salishan, Shekhar Borkar has made a very interesting statement at the end of these two sessions that we mentioned, the panel and ECP, and also the using exascale supercomputers. And he asked the question, does exascale actually exist? So do we have a significant number of sustained exascale applications? And the answer was mixed to some extent. And actually, I want to give you another answer in addition to the answers that were given at the meeting, because I want to give you an answer that is related to what Dan Reed said in his keynote at the conference. One of his major points he makes that innovations in transistors are still key to progress in HPC. They have been for the longest time. Many people are saying Moore's law is stopping. I would claim that Moore's law is somewhat stopping if you look at the constant. Many people say Moore's law is slowing. I wouldn't call this Moore's law, but the exponential increase is still continuing. It's continuing at a slightly lower rate. So in some sense, we are still building better and better transistors. One of these better transistor technologies is the gate-all-around silicon nanoribbon field effect transistor, which is in investigation today. It is going to go into production relatively soon. So there was a very nice paper 2024 on this that outlines the whole transistor with the gate and the oxide and the whole structure, the silicon nanoribbon channels. And this is at a relatively small scale. So the width of these inner channels is about 1.5 nanometers. The major problem in these transistors is actually that they're overheating. So they're simply melting if you run them at too high frequencies, if you trigger them too often, because there is of course some loss in the voltage. Some loss as they switch on and off. They're not energy neutral devices, so they do heat up. But now the question is, how much can we allow them to heat up without them losing their functionality? In fact, more than 50% of the failures of chips today are due to overheating. So this is a serious problem. They simply die over time. So what we did with partners, Mathieu Luisier, Alexandros Nikolaos Siogas, over at the EE department, is that they modeled this complex chip, and they actually built a very precise computational model, and then they simulated the heating patterns of each of those channels. And this allows manufacturers and engineers to use these simulations and to use these insights to build better transistors and to still drive the future of high-performance computing and AI forward. So that's quite interesting. So now let's look at this. But what does it mean? Well, we have to actually simulate the whole transistor, because we're still pushing these improvements at about 15% performance and 30% power efficiency over generation. But this is getting more and more complicated as we go along, so we have to pull more and more tricks. As you look at this very, very complex structure, if you look at the first transistors, they were somewhat trivial compared to this structure. And now we need to understand all the details to build the best possible physical layout, like super small, nanometer scale physical layout of this device. And at the very first simulation, we could only simulate a very small fraction of these nanowires. Actually, a couple of years ago, we managed to simulate, together with partners, of course, and again, Mathieu Luisier and Alexandros have been instrumental in leading that effort. We managed to simulate more than 10,000 atoms. And this made us the Gordon Bell winner in 2019. So we used the technology that we call data-centric parallel programming in order to achieve this, in order to resort the loops to be closer to optimal. And we, at the end, achieved a speed up of more than 100 times and a capability improvement of more than 100 times over the existing technology. So now, this year, we actually achieved a new result. So that's five years later, maybe 6 years later, depending on how you count, but it's really 5. We managed to simulate 25,000 to 42,000 atoms, which is essentially nearly a full transistor, as you can see here from the visualization. And this is quite nice. So how did we do this? Well, we ran the full system on the full simulation on 9,400 frontier nodes, MI250X, which is 98% of the frontier system. We managed to run 25,000 atoms and achieved true exascale, sustained exascale, 1.06 petaflop per second, 1063 petaflop per second, which is nearly 80% of the theoretical peak of that device, which is just a little bit above an exaflop per second. Keep in mind that this is all FP64, so full or double precision performance. So this is great. The first sustained exascale transistor simulation demonstrated, and we even do it for a very useful, strong use case that is driving transistor development pretty much directly. But now, this was in the context of the ECP, the Exascale Computing Project, because that machine was built in the auspices of the Exascale Computing Project. We also ran it on our machine in Switzerland, just with 2,600 ALPS nodes, which is about 97% of the machine. We were able to run a larger configuration, 42,000 atoms, which is now really covering the whole chip at a lower performance. So that's only 217 petaflop, but the larger system, larger capability. Why is that? Well, this is actually the biggest, not the fastest, but the biggest recorded transistor simulation today. And it's nearly the whole device, as I mentioned. And now the question is, why did we not run this at this size on the frontier node? Well, because the memory subsystem of the ALPS nodes, as I mentioned before, the nearly 20 terabyte accessible memory per node, make it much easier to access this memory, make it much easier to program that machine and to run these codes. So you could now argue, well, at the end, Grace is just a memory controller because we're not really using that machine. Well, I want to give you a little bit deeper insight into another application. So now I want to switch gears away from the transistor simulation to climate sciences, another application that uses the whole structure of that machine. So, and this application is simulating the Earth system, which is in fact the most complex simulation I have ever seen. It has varying scales and it's a chaotic system, which means even the smallest change in the input can produce an arbitrarily large change in the output. The spatial scales range from millimeters, like this size, to thousands of kilometers, planetary scale. The temporal scales range from seconds or even fraction of seconds to decades as we talk about climate change. And we need to simulate all kinds of things, like all of us humans essentially should be part of that simulation. And just to look at the complexity of the Earth system, I wanted to show you this picture. In fact, this is Giri Chokapalli. We took that picture at the Salishan meeting during a free break, essentially. And Giri is one of the architects of the GH200 chip. So I just wanted to make sure that we appreciate that. The GH200 chip is quite complicated, Superchip, it's quite complicated. But here in this picture, you can see all the elements we need to simulate. You can see the ocean. You cannot really see the ocean biogeochemistry, but believe me, it's in there. You can see the land, you can see a city, you can see the atmosphere, and you can see the vegetation represented by grass and trees and different vegetational characteristics. So and this is, as I mentioned, this extremely complex system, the most complex system I have ever seen in simulation. So what do we need to do? Well, we have components of the simulation. We simulate the atmosphere because it's a fluid to some extent. I mean, it's a gas. We simulate the land separately because it's developed by humans, it's developed by plants, it's inhibited by animals. So we have to simulate this as you go larger time horizons, because if it stops raining, the flora and fauna will be changing. So forests may disappear, deserts may appear, but if it starts raining somewhere else, a desert may actually turn into a forest. So that's quite important. So we have to model the full vegetation as well. We have to model the ocean, as I mentioned. About 70% of our planet is ocean. Much of that ocean is actually ice at the poles. And we have to model the ocean biogeochemistry, because that has an incredible impact on the CO2 emission or absorption of the ocean, as we will see in a couple of minutes. So anything less than that is not realistic for climate timescales. We have to model a whole interaction between at least all of those 5 players in there. And we did this in a simulation that is actually developed by the Max Planck Institute Max Planck Institute for Climate Research under Björn Stevens, together with the DKRZ and the DWD. And it's called the ICAN, the icosahedral non-hydrostatic Earth and System model, which has multiple pieces: the atmosphere model, the ocean model, and the land model, and then of course also biogeochemistry. All of those pieces together form a very large code base, and this is extremely complex because they have to simulate all of these different pieces. But now much of that is actually written in Fortran, pretty much all of it, and it's composed by 1 million lines of Fortran code. So now what we did together with our partners is to map this 1 million lines of Fortran to a Grace Hopper device, to this very complex CPU. But the nice thing is that we take the complexity as an advantage, because many of these components map directly to specific pieces of that chip, and we can use these pieces nearly for free. So let's look at this. Well, how do we map it? So on the GPU, on the CPU, we actually map the ocean and the ocean biogeochemistry, because they live at very slow timescales. They require a very, very slow update compared to the atmosphere, and they can totally run in that environment. Furthermore, they are also already written in OpenMP only, so that means they wouldn't even run on the GPU. But now, on the Hopper GPU, we have all of these OpenACC pieces, atmosphere, land, and vegetation, that are of course tightly coupled. And on the atmosphere part, we use our own programming framework, the data-centric parallel programming framework, to make it even faster. So we achieved significant speed-ups for pieces of the atmosphere component, I mean very large pieces of the atmosphere component, making it nearly twice as fast using that compilation framework, going from the unchanged Fortran code right to GPU code without any OpenACC directives. Actually, in my group, what we are trying to do is we are trying to expand this scope that we can compile the whole code, the whole 1 million lines of Fortran, unchanged, directly to GPUs. Now, what is the size of the simulation at planetary scale? We run it at a 1.25 kilometer resolution, which means every 1.25 kilometers approximately has a grid point that represents many of these variables. So for example, in the atmosphere, we have temperature, pressure, wind speed in various directions, and so on. So now the atmosphere alone has 347 billion parameters in that sense, 2 billion for land, about 24 billion for the vegetation, because there are many different plant types. And that we have to run at a time step of 10 seconds. Then on the ocean side, we have 86 billion for the ocean, and the ocean biogeochemistry is 326 billion, but they run only 6 times slower time stepping, so that's only every minute as a time step. So this whole model together actually has a total of 780 billion FP64 parameters, which is larger than the largest public AI models today. So this simulation is very, very challenging. We always say how big the AI computations are, but actually this model has more parameters and is bigger and is running for 30 years in a time step of 10 seconds. So it's quite demanding. And we achieved a speed on this device, the Grace Hopper device, again on the configuration I stated earlier, that's our ALPS machine, that is 33% faster than the fastest run that was recorded at a similar resolution today. And we achieve 82 simulated days per day, which means a 30-year campaign would take us about 3 months, maybe a little bit more, maybe 4 months to complete. And that is actually feasible now. And that includes all of those components. In fact, we get the ocean and the biogeochemistry for free, because most applications that are running today on these devices are not really using the capabilities of the Grace CPU. So in some sense, putting these together, taking advantage of the application complexity to exploit the Grace Hopper Superchip, gives us many benefits that would otherwise not be possible. So just to show you a little bit what impact that has, I want to show you this animation which looks at the ocean uptake and outgassing of CO2. So if it's red, the ocean is emitting CO2. If it's blue, the ocean is absorbing CO2. And you can also see in magenta these various wind speeds. And now you already see that there is an interesting relation between the winds and the outgassing and intake of the ocean. And that is actually what drives the simulation, and that's what makes the system quite complicated. So you can see some cyclones here. There is one happening right there, and that's actually moving the CO2 and mixing it up. And that system, or that overall system, makes it quite complicated to really measure the CO2 and predict the CO2 distribution over the Earth, and also the absorption and outgassing of the ocean. And at the end, the ocean is one of the biggest contributors, or actually potential absorbers, of CO2 in our planet. So that's quite important for us to understand. So with that, I would like to conclude. And what I mentioned is the complexity of the Grace Hopper Superchip. I talked about one of the first, or actually the first, exascale transistor simulation that can run at full sustained exaflop per second performance at FP64 on one of the largest machines on the planet, the Frontier machine. And it also runs on the ALPS machine, and it runs the largest transistor simulation ever performed. We looked at the modeling of the Earth system, and we looked at the record-setting modeling of the Earth system, so the fastest recorded performance to date on a full Earth system simulation, which is actually capable of executing a full campaign over 30 years at a reasonable cost today. And if you want to understand the Grasshopper Superchip in more detail, I would recommend you looking at that paper. That is a great write-up, a great analysis that shows you exactly how these memories behave and how they work together. Thank you very much.